Every time you sit on a commercial aircraft and feel that surge of power pushing you back into your seat, you are experiencing one of the most extraordinary pieces of engineering ever created, the jet engine. It weighs over 5 tons. It produces over 100,000 pounds of thrust. It operates at temperatures exceeding 1,700 degrees Celsius. And it does all of this while being certified safe enough to carry you and 300 other people across an ocean. Here's how it actually works. At its most fundamental level, a jet engine works by Newton's third law. Every action has an equal and opposite reaction. The engine pushes air backwards at enormous speed. The aircraft moves forward. That's it. That's the principle. But the engineering required to make that happen reliably, efficiently, and safely at 35,000 feet? That's where it gets extraordinary. The jet engine is a continuous internal combustion engine. Unlike a car engine which fires and pulses, a jet engine burns fuel continuously. Air goes in one end, gets mixed with fuel, burns, expands massively, and exits at the other end at high velocity. The difference in velocity between the air going in and the air coming out, that's what generates thrust. The jet engine works in 4 stages. Engineers call it suck, squeeze, bang, blow. Let's start with suck. The fan at the front of the engine pulls massive volumes of air in. On a large turbofan engine, we're talking about pulling in enough air to empty an Olympic swimming pool every 2 seconds. The fan blades are highly engineered aerofoils, the same principle as aircraft wings. They accelerate the air and direct it into the engine core. On a modern turbofan, a significant portion of this air, up to 80%, actually bypasses the engine core entirely. This bypass air is what generates most of the thrust and is also responsible for the turbofan being significantly more fuel efficient and quieter than earlier jet engines. Stage 2, squeeze, also known as compression. The air entering the engine core is compressed by a series of rotating compressor stages. Each stage is made up of rotating blades, rotors, and stationary blades, stators. The rotors accelerate the air, the stators slow it down and redirect it into the next stage. With each stage, the air pressure increases and the temperature rises. By the time the air reaches the combustion chamber, it has been compressed to between 40 and 50 times atmospheric pressure. The temperature is already around 600 degrees Celsius before any fuel has been added. The compressor is arguably the most mechanically complex part of the entire engine. Hundreds of precisely machined blades spinning at thousands of revolutions per minute, with clearances measured in fractions of a millimeter. Stage 3, bang. Combustion. Fuel, typically Jet A or Jet A1 kerosene, is injected into the combustion chamber and mixed with the compressed air. It is ignited by igniters, similar in principle to a spark plug. The mixture burns continuously and the temperature rises to between 1,500 and 1,700 degrees Celsius. That is hotter than the melting point of the turbine blades themselves. The reason the blades don't melt is extraordinary engineering. They are cooled internally by air bled from the compressor, flowing through tiny channels inside the blade. Some turbine blades are also coated with thermal barrier coatings, ceramic layers that insulate the metal from the extreme heat. The combustion gases expand massively and exit the combustion chamber at extremely high velocity. Stage 4, blow. The high-velocity combustion gases pass through the turbine stages. The turbines extract energy from the gas flow. This energy is used to drive the compressor and the fan at the front of the engine. This is the elegant genius of the jet engine. The engine powers itself. The turbine is connected to the compressor by a shaft. The energy extracted from the exhaust drives the compressor, which compresses more air, which feeds more combustion, which drives the turbine. A self-sustaining cycle. The gases that exit the rear of the engine, the exhaust, are still moving at extremely high velocity. Combined with the bypass air from the fan, this generates the thrust that moves the aircraft. Every stage connected, every stage dependent on the others. Now, the engine I've been describing is a turbofan, the most common type of engine on commercial aircraft today. The key feature is that large fan at the front, which generates the majority of thrust through bypass air rather than pure jet exhaust. The ratio of bypass air to core air is called the bypass ratio. Modern high bypass turbofan engines, like the Rolls-Royce Trent or the GE90, have bypass ratios of up to 12:1. That means for every kilogram of air going through the core, 12 kilograms go around it. This makes them dramatically more fuel efficient than earlier low-bypass engines. It also makes them significantly quieter, which is why modern aircraft are far less noisy than the jets of the 1960s and 70s. The turbofan is one of the greatest engineering achievements of the 20th century. So what can go wrong? Quite a lot, actually. Bird strikes are one of the most common threats. A bird ingested into a running engine can cause significant damage to the fan blades and compressor. This is why FOD, foreign object debris, is taken so seriously at every airport. Compressor stalls can occur when the airflow through the engine becomes disrupted. The engine loses its stable operating condition and can surge. Turbine blade failures, oil system issues, fuel system problems. All of these can cause an engine to malfunction or shut down in flight. But here's the critical point. Commercial aircraft are certified to fly safely on one engine. Every procedure for every engine failure is trained, documented, and practiced. The engine is designed to fail safely. And when it does fail, it is usually caught long before it becomes catastrophic. By engineers, in maintenance. As an aircraft maintenance engineer, jet engines are the most technically demanding systems I work with. Engine runs, bore scope inspections, oil analysis, vibration monitoring. These are the tools we use to understand the health of an engine before a problem becomes a failure. A bore scope inspection involves inserting a tiny camera into the engine through access ports, without disassembling it, to visually inspect the compressor and turbine blades for cracks, erosion, and damage. Oil analysis can detect metal particles in the oil, an early warning sign of internal wear before any external symptom appears. These inspections happen on a strict schedule. They are not optional. They are not rushed. Because the alternative, an engine failure at 35,000 feet, is not an outcome anyone is prepared to accept. So now you know how a jet engine actually works. Suck, squeeze, bang, blow. Newton's third law, extraordinary engineering. If this changed how you think about the next flight you take, hit subscribe. I break down aviation in a way that actually makes sense. See you in the next one.